All right, so now we're going to continue the lecture on integrity, namely MACs and digital signatures. So last time we saw about how to construct a MAC, namely AES-EMAC. So now we're just going to revise it a little bit and then ask some other questions and think a bit more about how we can use it and what else we can construct using it. So a brief recap on AES-EMAC. So the way it works, the way you do the MAC for a message is, as usual, you're going to split your message into plain text blocks. So again, this sign is concatenation. And then you're also going to have your keys consisting of two block cipher keys. Okay? And you're going to take P1 and you're going to pass it through AES sub K1. And then you get S1. And then you're going to XOR that with P2 and pass it through AES sub K1 and so forth, all the way until the very last plain text block. Which you then pass into AES sub K2, and that gives you out the tag. Okay. So last time we asked a bunch of questions about the MAC to understand why you need the second key, namely why you need this terminating the last application of the block cipher with a separate key. So T is the final MAC. And we saw that the reason is that if you don't have this, you can do all kinds of tricks to forge a MAC. If you just have the first n elements, you could do things such as extending the MAC, or you could change the message around here so that you obtain the similar MAC. So this was very important to mark the termination of the MAC. So now a few questions. One question is, so this is a MAC, right? It's meant to be unforgeable, existentially unforgeable. No attacker should be able to forge the MAC for a new message for which they have not seen a MAC. But a question is it collision resistant? By looking at this, is this collision resistant? So remember from hash functions, the property, something is not collision resistant if an attacker can find two messages that hash to the same value. So if for a moment we would look at this MAC as a hash function, is it collision resistant or not? So remember that the hash function doesn't have any secret. Right? It doesn't have any secret. So if you take, so I'm saying consider a hash of M to be the MAC with some key K and the message M. Okay, so this will be part of the hash definition because the hash function doesn't have any secret, everything is known. So then, basically, if this is part of your hash function, then it's known to the attacker. Okay, then it's known to attacker. Well, if the key is known to the attacker, then how can the attacker find a collision? Definitely, so you said one such possibility. And how? Well, if they have the key K, then it's super simple to find a collision, either by saying, okay, this is one of your messages that T is the final result, or it can say, this is another message, which is P2 XOR with S1, and then T is the final result. So basically, this is the collision. The collision is between P1 concatenated with P2, and then S1 XOR P2, right? This could be just, that's it. So this is a one block, and this is a two block message. They both would lead to the same, and then you can have the rest of the blocks. They both would lead to T. Okay, so if the attacker has the key K, they can compute S1 because S1 is just the block cipher applied to P1, and you can check that these two messages lead to the same tag T. So essentially, the attacker found a collision. That's a very good point. Is this only under the assumption that K is known to the attacker? Well, I wouldn't say only, but definitely under the assumption that K is known to the attacker, this is not collision resistant. Now, if K is not known to the attacker, then it's not really a hash function, right? Because a hash function, everything is known to the attacker. So you could have a keyed hash, and then you could make things safe. Okay, that's something else. That's a different construct, but that's a good question, yeah.